Good afternoon and welcome to Chemspec Europe's digital presentation series. This afternoon, we bring you Arxada's webinar on harnessing atom-efficient chemistries for greener customized solutions. Before I introduce Arxada's presenters, I would just like to remind you that this session is being recorded and also that we would like to invite all of you to write questions into the question box on the dashboard. And we will have time to go through these questions later in our Q&A session. If we don't get through all of the questions, then someone from the Arxada team will be in touch with you in the next few days. So without further ado, let me introduce you to today's speakers. We have Jan Mees. Jan is Head of New Business Development CDMO. We have Luisa Sebastian, Senior Chemist in Process Development. We also have Marie Hoffmann, Manager Business Development CDMO, and we have Ulrich Meyerhofer, Head of Technical Evaluation and Development. So I will hand over to Jan Mees, I think, who will start. I will just need to click a button and then Jan will be able to share his screen. Perfect. So currently we see a blue screen
coming up. Give me a second, please.
Exactly. Let's just wait a few seconds.
You should be seeing my screen now.
Yes, perfect.
Okay, good. So then welcome everyone also from my side. Thank you very much, Lily, for the introduction. Today I'm joined by Arxada's finest, and we want to tell you a little bit about our latest solutions for greener chemistry and for atom-efficient chemistries. This is part of our CDMO offering, and we're very excited about this. But before we really get into the presentation, we have a very small poll for you, our audience, just to find out what struck your interest when you signed up for this webinar. It's our first, so we were very interested and keen to learn what is it that draw you in to this call today. And we will try, when we get your feedback, to kind of incorporate it when we talk about our individual elements. So please, dear Kempe, can you bring up our poll?
Yeah, can you see that now? It should be up. So what caught your attention and made you decide to join us today is the question. So the answers are Arxada, this new company with 125 years of history, our efforts towards sustainable atom-efficient processes, our late-stage fluoroalkylation, the scope of our copper-free Grignard reaction, and Arxada's dione salt insights and cyclobutanes. So we'll give that a few seconds and see what comes in. So we're at 57% have voted so far. Give it a few more seconds if anyone else wants to answer. 70%. So yeah, I think that's it. So I'll close the poll and share the results. Back to you, Jan.
Okay, thank you very much. So basically the results are in, and basically what we see is a high interest in Arxada, the company, which 50% and 56% towards the sustainable solutions, a little bit less for the fluoroalkylation. The scope of our coppers is at 25% and 13% for the dione salt. Thank you very much. So we will accordingly try to pace our presentation just to make sure we have everything that you want to see and want to hear about. Again, to repeat what Lydia has said at the beginning, if there are any questions and if there is any interest, please reach out to us after this webinar. So without further ado, now jumping into the presentation, and this presentation will end with an invitation to talk to us. What we're doing here is quite clearly a snapshot of what we can say and do at the moment. Everybody knows that CDMO is by nature very secretive. You cannot openly talk about your successes, about your customers, about your efforts. So what we have done is we have tried to give you a glance of behind the curtain, what is normally not shown to the public, by showing you areas we're working on which are not customer specific. They just give you a general trend, a general impulse or push we're doing, but they stand for much more. They stand for the 1,000 plus solutions we've developed over the past years. So please see them as such. See them as our effort to show you what we can do very precisely on these topics, and they have caught your interest. They're the reason why you're here. But also please see them as a general approach of Arxada CDMO towards atom efficiency and towards greener chemistry. And these are merely snapshots or examples of the general trend, which is the red thread or the lifeblood of our company. So looking at Arxada, which may be a new name for you, it surely is a new name for us. It's been around since 6 months, but the company behind it has been around for 125 years plus. So we are a spin-off, if you like, sold formerly specialty chemicals, specialty ingredients by Lonza. So our history dates back to the 220 years ago. Now we are standalone company based it's still in Basel, with the heritage of a companies which have been around forever and the agility and the energy of a startup, of a new company. And we wanted to harness both those elements, and that's essentially what is Arxada. If you look at it from a controlling or from a financial standpoint, you see that there's more than 3,800 employees. There's quite a few R&D centers and even more manufacturing sites, 26 in total. And these are all split into two business units. One is microbial control solutions, and the other is specialty product solutions, of which CDMO is a part of. Zooming in into these two business units, you can see that microbial control covers everything from hygiene, wood protection, crop protection, and home and personal care, amongst others, whereas specialty products is composites, performance chemicals and intermediates, and as mentioned, CDMO, which is the business line you're talking to today. So what is CDMO at Arxada? I've mentioned before, we're coming from a long lineage of successful projects in many, many different industries. And as you can see, they're quite extensive. So it's not a focus of one particular industry. Arxada, or formerly Lonza, has focused on anything from food and nutrition to agriculture, cosmetics, energy storage, fragrances, personal care, you name it. We've found solutions for customers in all these areas. And we found solutions for customers who are chemical companies themselves since many, many years in the industry. But we also did find solutions for startups or companies, rising stars, who are just at the brink of bringing new innovation into the market. Zooming in, and just to give you success stories, again, just to mention the secretive nature. So unfortunately, we can only here also show you a little bit what is behind the curtain. But luckily, we have two success stories which we can name, because the companies behind choose to make a public announcement with us, which we're very grateful for. To zoom into our success stories, from the personal care, we are very strong in the sun protection area, and we have some very interesting UVA filters, which is approved, as you can see, in EU, Mexico, Japan, and Taiwan. moving to food and beverages, we helped the company Geltar, a very interesting startup from California, North America, to bring in the first vegan collagen into the market, which is an incredible push away from animal-derived collagens. And we're very proud that we were a contributing factor to their success. Turning to agro, we cannot mention who, but we were the first to market in the product class herbicides, bringing really from lab to life in a very comprehensive and a very fast manner. And lastly, again, fortunately, we're able to mention the company by name, Natron Energy, an incredible startup yet again, who was right now attempting to disrupt energy storage for certain parts of the industry, namely the data centers. And we're very fortunate that they teamed up with us, and we are bringing them solutions which they've never accomplished before, and really from lab to a large scale in a matter of very few months and years. So with this, I hope I was able to tease you for what is yet to come, and I'm very happy to hand over now to Marie.
Thank you very much, Jan. So before jumping into the specific topics, first of all, I would like to thank you for being here, but I would also like to give you an overview of how we work and what we can bring to your project. So obviously, as CDMO, our aim is to go up to the production scale with you, our customer, in order to produce multi-metric ton of a product which is going to the market. However, we can start at different stages. So sometimes we talk to people with a process that is already well established, already working on multi-metric ton scale. In this case, we go just for tech transfer to production. But sometimes we're also working with people very early stage with a few grams out of the lab, in which case we need to undergo all of these steps, which are process development, optimization, scale up, tech transfer, and production. So there is various entry points, and we are happy to consider them all, whatever you need. Besides this classical way up to the market and to the production, we also offer a variety of additional services. Okay, such as, for example, stability testing and regulatory support. And all of this we make available if you don't have the resource internally, just to make sure, once again, we will reach the market as quick as possible with the full package. So how we do produce, where we do have two sites that are dedicated to our CDMO business line. One is working and focusing on chemistry that we're going to discuss today. This one is located in the south of Switzerland in Visp. And the other one is focusing on biotechnology, or everything which is fermentation process related. And of course, we have the option to mix both where there is an opportunity with regard to your project. But let's focus for today on the chemistry. So, as already mentioned, the site is located in the south of Switzerland in Visp, and it is indeed a R&D and manufacturing site, which is working with a highly flexible production concept with multi-purpose plant. Over there, we do exclusive manufacturing of advanced intermediate and active ingredient. The site is backward integrated, as we're going to see in a minute. We have an integrated waste and energy management facility, and we work with different quality standards in order to make sure we can reach different type of markets. Of note, on site, we also do produce and supply non-exclusive key building block for our performance intermediate and chemical division, which also belong to Arxada. So in terms of capability, what can be found on site, we have 5 highly flexible and interconnected chemical multipurpose complexes with 22 plants. The reactor size overall is 670 cubic. We have reactor ranging from 5 to 16 cubic. We use various material of construction, such as alloy, glass line, or stainless steel, here again to allow a variety of chemistry to be performed. The quantity we can work with on a given project for each campaign and each year goes from 5 to hundreds metric ton. We work with different temperature, with different pressure as well. And in terms of technology and chemistry we can work with, here again, it's very diverse. So we can do CC, CO, CN bond formation, cross-coupling, homologation, quaternization, substitution, you name it. But the easier is that you give us a call and we tell you a bit more about what we can do and if that will work for your project. So with regard, Sorry, my slides are struggling just a little bit to go. Okay, so with regard to this backward integrated system we have on site, our chemical network, what we do is we actually produce ourselves a variety of small molecule or reagents such as CO2, ethylene, acetylene, methane, or H2, for example. And as you can see here, we use this small molecule and reagent and develop several types of process with it. So for example, if you do follow this black part of the screen, thanks to this, we're able to synthesize various aniline or various pyridine, for example. We also access various compound with nitrogen in it on the right. All of this allowing to broaden the scope of what we can do in terms of chemistry. And what's interesting as well is that quite sometimes these small molecules, they are not all on this slide, but some of them are not transportable, or the transport is quite expensive. Therefore, if this is something you need into your process, you will have to buy first an advanced intermediate in order to develop this process. Whilst as we do generate those on site, it can be injected directly into a process in order to speed up, once again, time to market and make sure we are as efficient as possible to develop a process. So something which is not mentioned here and that we also do produce on site is indeed the ketone and diketone chemical network, but we're going to tell a bit more in a minute about it, so we'll leave it aside for now. This is basically the end of this generic Arxada CDMO introduction. If you want to know more, please ask in the Q&A or contact us later on. And right now we're going to focus on 3 specific topics that we develop, and we hope that it will highlight our proactive and sustainable approach towards a greener customized solution. So now the stage is for Uli.
No, for me.
Luisa, perfect.
Thanks, Maddie. And thanks to our audience for being here today. In my part of this webinar, we will present to you fluoroalkylation. We will start with the introduction about this field, what type of fluorochemicals are on the market, how much this field is increasing in the last few years, and then we'll go into discussing why is it so important nowadays, these chemicals, what is the approach, which is usually followed by research, and what is our approach, which is more towards sustainability and introduction of this fluoro at a later stage. So let's see. Okay, good, it works. So yeah, a bit of a backup information. What type of compounds do we have currently in the market? What are these fluorochemicals? So here on the left, you can see a graph of what is typical in the market, what carbon fluorobonds are present in the compounds which contain these fluoro moieties. And on the right, you can see a graph where the number of publications per year is represented. As you can see, this is a field which is increasing exponentially in the last few years. And seems to be that in most cases, the synthesis follows a downstream approach, which means you usually use a starting material which contains already the fluoromoiety instead of introducing later. What happens with this approach is the fact that you're very limited with the amount of starting materials you can use. There are only a few available, and you might end up with a very lengthy synthetic route plus a very expensive starting material. Next moves. Okay, why is fluorinated chemistry so important nowadays? Well, fluorine had some unique properties. Fluoroorganic compounds are highly stable, which is something very desired for a compound you want to get into the market. And the key might be because fluoro is a good replacement for hydrogen and hydroxy moieties, which means that you can play with fluoro to make your molecule with the right properties in terms of lipophilicity, pKa, and so on. Maybe because of this, we see that nowadays 20–30% of the agrochemicals and pharmaceuticals nowadays contain fluorine. Not only there, You also find them in surfactants, solvents, lubricants, liquid crystals, you name it. Unfortunately, these compounds are usually not found in nature. They need to be synthesized. So all those building blocks that you will start your synthesis with, they already have to be synthesized. Our approach would be to develop new methods to introduce this fluorine later, which means you have more freedom to choose your synthetic route, to choose a short synthetic route, and later introduce this fluoromoiety via a catalytic method. As an example of what an impact this has, I'm representing here the synthesis of a trifluoromethyl nicotinic acid, right? So you can see in the scheme above, you have 4 synthetic steps, starting from cyanoacetamide and acid trifluoroacetoacetate. As you might imagine, to get this simple starting material requiring already 4 synthetic steps, it means that you're gonna get a very expensive starting material. 5 grams costs 125 euros. This is prohibitively expensive, I would say. And on top of that, the more synthetic steps you're gonna have, the more waste you're going to generate. So it would be much better from a conceptual point of view to actually start from nicotinic acid and in one catalytic stage to get to the desired product you want to obtain. Right. So to develop new synthetic routes, of course, we have the traditional academic environment, and there is also industrial environment. Both can do development. They are slightly different. In a academic environment, the focus is slightly different, right? What is the target? The target is a publication. So to get a publication, you might be more interested in new chemistry. Of course, it's very exciting, works for the first time, might get you a nice publication. Big quantities are not necessary. A few milligrams will be enough just to get a good characterization of your molecule. And you're likely to use one of the reagents that you see here, these popular reagents of late stage fluoroalkylation. From these big reagents, the only part of the molecule that you are actually introducing in your reactant is just this CF3. If you look at the molecular weight of the CF3 compared to the molecular weight of the reagents, you get an idea that actually most of the reagent, which you're also using in stoichiometric amounts, is waste. From an industrial point of view, we are not so much interested in innovative reactions, but new processes, right? So we will focus more on other things such as safety studies, because if you're gonna produce this in tons, you want to make sure it can be produced, right? So safety is something you're gonna be looking at right from the beginning. You're gonna be very interested to make sure this is always working consistently. You want a robust synthesis because you need to produce tons of material in specs also. Everything needs to be documented, traceable. If you get a problem later on in the use of this material or further synthesis, you want to be able to track it down to know what happened to prevent it to happen again in the future. And big focus, cost and waste generation, which is not, of course, not a matter of concern when you're in academia. But if you're producing in ton scale, you're also going to produce tons of waste. So this is a big issue. For this reason, if you look at the reagents that we would be using preferably in a late stage alkylation, is the ones you see on the right, where most of the reagent is actually being introduced into your molecule in order to generate as little waste as possible. Both sides, academia and industry, has advantages. I'm only saying if you want to get a product or a process to be done in plant, it would be a good idea to also involve industry. Of course, it's better if you have the best of both worlds. So this means a collaboration between both of them. So you get the state of the art from the academia, and you get the focus towards production from the industry side. And this is what we try to do. It should come in the next slide. Doesn't? Okay, did I go too far? Yes. Okay, good. So this is what we did as a collaboration with academia. So we developed such a process in which we introduce our fluoro moiety at the end using a catalyst. We started with palladium platinum. So here you can see some examples. The references and the number 1 are the ones with platinum. The references and the number 2 are the ones with palladium. So as you can see, we get yields between 80, 94, 70%, moderate yields. And then we went to get it even better for a process point of view, which means like using cheaper non-noble metals, which is much better nowadays given the price of this platinum palladium catalyst. And as you can see here, the process was also developed using cobalt and nickel, and where also moderate good yields can be obtained. And yep, here below you see the number 1 are the references with cobalt, and number 2 are the references with nickel. So this is an example of how we think things should be done. So for a synthetic group in which you might have fluorine in your compound, instead of having to buy that starting material which already contains fluorine so expensive, you might want to consider this approach, which could make for a cheaper route and shorter, generated less weight. So this is our approach to this kind of chemistry. And with this, I will hand over to Ulrich for some copper-free, exciting chemistry.
Thanks, Luisa, for this. So the next part of our talk, we would also like to start up with a fun question to the audience. And
yeah, right. Let me launch the next poll question. So the next question, sorry. The next question we have is, which metal has the largest share in causing heavy metal pollution in our oceans? And the possible answers are lead, mercury, and copper. So again, we'll leave this open for just a few seconds to give everyone a chance to choose one of those 3 possible answers. We're at 63%. Yeah, still a few coming in. Right, last 5 seconds, and then I will close and share the results with you. Okay, and there we go. I'll hand back to you.
yeah, thanks. So keep that in mind. We will have the answer on the next slide. It might be a bit cheeky because our title or our next topic is about copper-free. And and here you have the answer. So we developed a copper-free process based on Grignard chemistry, but actually copper only is coming in 3rd, and the majority of the pollution in our oceans is actually lead, followed by mercury, but copper is nevertheless with almost 10% quite still significant industrial input from human activities. And just keep in mind, from all the heavy metal pollution we see in our ocean, only 4% have actually natural origins, and all the rest is due to human origins and the way we are doing our work. And so that's for us pretty clear. We want to be a sustainable chemical company, and whatever heavy metals we use as catalysts or as reactants in our chemical processes, they need a proper wastewater treatment or a proper waste treatment at all. And so for us, it equals using heavy metals is related to costs, whatever type of treatment we will take on. Yeah, there are several methods, for example, for copper, that every single method is related to costs. And if we go on to the Grignard chemistry we are talking today, it's a quite well-known and old type of chemistry, the Grignard chemistry. It works quite fine, but the traditional way really to make ketones based on Grignard chemistry is applying carboxylic acid chlorides, and they are more or less dependent on. Can we go back? Jan, can you go back to slide? One more. Sorry for that. Yes, they are really requiring in most of the cases copper chloride as a catalyst, and the reason is that actually just with the Grignard reaction, the reaction is quite unselective and the yields are not very high, and you tend to see significant accumulation, which also relates to process safety risks. The reaction with acidic chlorides is well described, and there are several publications describing it. And what's suggested is that you have like a catalytic cycle that we have depicted down here, and that the actual active species in the reaction are cuprates rather than the actual Grignard reagent. So what we did in the past is, Arxada, we are a new company, but with an old long legacy in the chemical industry. So we have a proven track record in Grignard chemistry, and what we can offer. So we have several Grignard protocols already established in production, and we are happy to find the right solution for your problem. But what we have developed so far, it's Grignard in batch processes and semi-batch processes, as well as in continuous processes such as like CSTRs, loop reactors, or in flow. So we are quite confident if you have chemistry related to Grignard chemistry, we are the right partners to talk to. And what we want to focus today is, how can we make Grignard chemistry even more sustainable? And so the focus, as mentioned today, will be the ketone formation with Grignard chemistry. And what we developed with our team here in Visp is it's quite a simple but move. We replace the acetic chloride by an acetic anhydride. It's not a totally new type of reaction, but in the past, if you look in literature, acetic anhydrides, they are often related with very or extremely low temperatures. The yields are mostly not very good, and so it's not really attractive to make it in large scale. So, but what we find out, that if you really have a good parameter control, you can achieve moderated temperatures, quantitative yields, and an extremely high selectivity without having to use any heavy metal catalysts. And what does that mean? It's illustrated here. It's the same molecule, which is depicted up here. Yeah, you have nice yields with the traditional method with copper chloride. But if you look at the atom efficiency, yeah, it's quite moderate with 54%, despite the really nice yield of 94%. If we now look at our new processes, you see the yields, they are even higher. That's because our reaction is actually, if it's optimized, more selective and forms less side products than the copper catalyzed variation. But we have a significant increase of the atom efficiency of our process. And for our fully optimized process, we almost achieve, we do achieve atom efficiencies of 98%. If you're now wondering, how can we achieve it? You will see it here. So what we are trying to do at Arxada is, we are trying to utilize our waste streams, or convert our wastes into usable and value streams. And how we did it in this case, we made the Grignard reaction. We are forming the salts, which is normally going into waste. We are neutralizing it, forming back the acid, getting a salt that has a market potential. So we built it up in the past and are still continuing to grow our industry network for different salt streams. And we found ways to bring magnesium salts into industries such like catalysts, electronics, de-icing applications, alloys, and also fertilizers. And the acid that's freed in the system can be reused within our ketene network into the starting material and the acetic anhydride, which can be reused as starting material in our processes. And that's now just to highlight our ketene and diketene network, which we can offer on site. As we have here our ketene that's based on our acetic acid. Here's the stream we described on the page before into our acetic anhydrides. And it also goes into diketene, where we have several offers in place, ranging from acetoacetates to beta hydroxybutyrates and other specialty chemicals. And quite a new addition to our portfolio here is the one up here, where we find a way to isolate and offer access towards cyclobutanone derivatives. And for this topic, I will hand over to my colleague Marie, which will introduce you to that exciting new pathway to access cyclobutanones.
Perfect, thanks Uli. So yes, this is now the last part where we're going to discuss this diene salt and how we develop this in order to close the gap towards cyclobutane derivatives. So maybe I'm going to be able to change slides. Okay, so the reason why we went with this topic is because first we looked at the literature, and indeed the number of patent fields containing product with cyclobutane substructure for different type of use. And as we can see here on this graph, over the last 20 years, there is an increasing number of publication and patent about this type of substructure. And this is now clearly be seen on the market as well, because indeed Pfizer just received very recently an approval for this JAK inhibitor, having a 1,3-diaminocyclobutane. And another example, Syngenta is currently studying this molecule on the right, which is a 1,2-cyclobutane derivatives. A compound is currently in development and is foreseen as a pesticide. So there is a real growing interest from the market for this type of substructure. We also read an interesting paper from the AstraZeneca team that was published a couple of years ago. So AstraZeneca as well did look at the number of drug substances patented, containing different type of small constrained cycle, such as cyclopropane, cyclobutane, oxetane, and a couple of others. So what can be seen here on this graph is that over the last 10 years, there is indeed an interest for this type of small molecule and small ring, but let's focus on cyclobutane. So AstraZeneca is even saying that the use of cyclobutane derivatives is indeed flourished, but what they are also saying is that the synthetic chemistry to access this type of motif remain underdeveloped, and this might be one of the reasons why we don't see more drugs and active ingredient containing cyclobutane derivatives. And this is very interesting to us because indeed, thanks to our ketone workstream, we know that we would be able to access cyclobutane. So we took a step back and we indeed look at the full value chain sort of this cyclobutane. So from market to the ID or from the ID to the market. So of course there is different stages, research, development and production, and these different people and group involved will need different quantity of material. So gram scale, kg scale and multi-metric ton scale. If we look at, for example, research, well, this building block containing cyclobutane are very much available. We can find many well-decorated cyclobutane building block from a variety of vendors. However, this is often based on complex chemistry, which will be not very well fitted for later large-scale production. On the production side, what we saw is that indeed we could access such cyclobutane thanks to our ketone and diketene work stream. However, because this reagent is not transportable, so going back to the chemical network, well, we produce it on site and have to transform it on site, it cannot be used early stage to do some sort of research. So what we saw is that there is indeed a gap in between, okay, making multi-metric ton scale of cyclobutane derivative, many different building blocks available in research, and in development, well, not so much. So we find out that indeed, at some point, project might be dropped if cyclobutane access is perceived as non-existent. So because we had this technology on site, we were looking for a way to fill this gap and avoid a project being dropped at this intermediate scale. And to do so, well, we find out a way to isolate and synthesize stable alternative of cyclobutadiene, which is a 1,3 substituted one, and we can now obtain it from gram to multi-metric ton. And of course, as you can see already, this is just opening the door for a variety of cyclobutane, because from that we can probably obtain many different type of building block and modifying chemistry-wise with ketone, amine, whatsoever, you name it. All of this building block can then serve as for synthesis of active ingredient, intermediate, and different other type of building block. So just an overview on the chemistry and how we do it. So as mentioned before, we do obtain ketone, which is an unstable material thanks to the pyrolysis of acetic acid. And this ketone itself is evolving and going to produce some diketene, which is again unstable, and some 1,3-cyclobutadiene, which is going to evolve towards triketene. And all of this material indeed have limited stability. So on site, it's quite easy to use because we can inject it directly. So for example, with diketene, we use it into our CDMO facility for exclusive synthesis, and our colleague from Performance Intermediate and Chemical use it as well to produce some reagents that are available from their catalog. But here again, this doesn't allow us to support you with this intermediate development stage because this is all unstable material and the process is going to have to happen fully on site from early stage to later stage. So what we find out is that we can actually derivatize this triketene in order to synthesize now this 1,3-cyclobutadiene salt, which is a stable variant of the compound you saw before. It can be isolated, it can be stored, it is an ice spotter, very much stable. And this is now opening the door to study a variety of different types of cyclobutane that can later on be synthesized on the CDMO side directly through the ketone and diketene workstream. So this product is now indeed available, and we made some of them. It's a 1,3-cyclobutadiene salt, which we see as a promising building block towards cyclobutane derivatives, thanks to different derivatization process. And with that, we hope to have no more gap between research and production with regard to the different cyclobutane containing molecule. So as a conclusion here, what we saw is, and the way we work is always looking at the market. So in this case, we looked at cyclobutane, but there's many other examples, such as the two other compounds that are shown on this slide, and we try to figure out, okay, well, there is an interest here with our asset, either something we can do to support our customer. Can we proactively develop something that will be helpful for their project? And this is exactly, well, hopefully what we just show you is a cyclobutane, but there is many more examples. And we know that our assets, so ketene, diketene, and triketene, would allow us to obtain all these compounds on the left, which all are a potential precursor for the product on the right. So now, what you saw is that we looked at the market, publication, patent in order to understand what can be missing and try to develop this accordingly. However, if you do feel that there is something missing for your project, for your research, well, there is an easy way to figure out if we can do it. And I will highly recommend, well, give us a call. We will have a think about it. And eventually we will see if we could develop something with regard to your project so that even this intermediate kg scale is available. And last but not least, I will hand over back to Jan.
Thank you, Marie. And it is now my pleasure to conclude the active part from us of this webinar and hand over the active participation of you, our dear audience. Thanks again for joining us, and thanks again for basically what will now try to do in the next couple of minutes before we do get to the questions from you is to kind of try to repeat the summary or the essence that what you were hopefully able to see. What you see is a company which has both a heritage and a long lineage into the chemistry. It has a link to the biotech, which makes it a modern company funded by private equity, Bain and Cinven, and a company with a heritage, a company who has chemistry, a company who has biotech in their portfolio. And we believe that makes us unique. We believe that back when Lonza CDMO invented CDMO in the 1980s, they came up with a solution to problems which were at that time novel and caught on and was imitated and copied by many other companies and further increased. And we now see it as our opportunity to bring you the next level of CDMO, which means that we can potentiate your performance, that's the slogan from Arxada, by taking you and taking your product by the hand, wherever you are, in process development or in a production, in the scale to scale, you want to have a secondary supplier. And if you are in any of these or other industries, we're here for you. We're willing to give every idea, every request you have a shot, and based on the know-how from everybody working at Arxada and the CDMO team, we're very excited to have your call. And of course, we are at Chemspec, you would imagine, so more than welcome to meet you at Chemspec as well. So before we leave you to the questions, we have one last poll. We would like to know what caught your interest and to see if Marie was able to convince you that the Dion salt is much more attractive than what just the pure name on the agenda suggested. So please answer our last question, and then we're up for your questions. So the poll is active, I think, Lily?
Yep, so it is active, and I'll just read it out. Which part of this webinar was the most insightful for you? And the possible answers are discovering Arxada CDMO, the late-stage fluoroalkylation, the copper-free Grignard alternative, and the Dion and its potential towards cyclobutanes. So we will leave this open for sort of 30 seconds, just to give everyone a chance to vote. Maybe another 10 seconds. That really should give everyone an opportunity to vote. Okay, I will close the poll and share the results with you. There you go. Back to you, Jan.
Thank you very much, Louise. So as you can see, the diane salt has caught on. Thank you very much, and congratulations, Marie, for making this topic very interesting for everyone. The rest is pretty much online and in line with what you were looking for beforehand. So thank you very much for your answers. We hope we were able to show you with these particular examples the way we operate, the way we work, the way Arxada wants to discover value together with you and hopefully potentially your performance. With this, I thank you on behalf of my colleagues here in this call and give it to you, Lily, for questions and Q&A session.
Thank you very much. So thank you to all of you from the Arxada team for sharing your knowledge here today. And as you said, now we have some time to go through some questions that have been coming in from the audience. So let me just have a look what has come in. Okay, so the first question we have is, what has changed for Arxada under private equity?
Okay, thank you very much. I'll take that. That's kind of my section. To be honest, at a service level, not very much. We do the same CDMO as before. I think more conceptually, private equity has high ambitions to grow and has a different view from a shareholder value, which is a quarterly way of looking at things, towards the private equity point of view, which is more of a multi-year point of view. So what we're seeing is a owner or two owners who are very active with us, who are really asking us, what can we do to support growth, and how can we support the long-term growth? Which means in return for our customers, our focus is not quarter by quarter, but for the long run, which we believe is a great thing.
Thank you, Jan. And the next question is, what are the future plans for CDMO under Arxada? I assume that's also for you, Jan.
Okay, thank you very much, Lily. Yeah, the future plans for CDMO is to, first of all, continue the offering that we have, to expand the offering that we have, to give our customers solutions like the ones we presented here, and to hopefully enjoy joint success. What we have, as I mentioned before, quite uniquely, is a linkage between biotech and chemistry, with both part of our business unit, and we would love to further explore that arch as well. Can we work on projects which actually require both fermentation skills and chemistry skills? So more of the same, and hopefully in a combination, even better.
Great, thank you. Next question, slightly more technical. Is the commercial use of waste salts limited to magnesium salts?
Yeah, I will take this one. The short answer is no. The real answer, it's difficult, yeah, because for magnesium salts, especially the example we showed, it's relatively easy because the magnesium salts have a certain value, and as you have seen, our chemistry is quite clean with very little side products, so that makes the purification and isolation quite easy. So it depends. We as Arxada, we have a network with industry partners who are interested in our salt streams. We are trying to increase and build up these networks, yeah, and offer several opportunities. But it really depends. Yeah, if it's a salt mixture, it's getting more difficult. So yeah, if it's a clean process, it's easy, but it's for sure not limited on magnesium salts. And we have several options, but it's always depending on the final process. But as part of our process development, yeah, we are looking at it, and we are confident that we can come up with a sustainable solution, but it's not guaranteed.
Thank you. We then have a question for Louisa. I had a question for Louisa. Can you generate novel IP around the beautiful fluorination chemistries that you are developing?
Well, I assume, yeah, if it's new synthetic route, new catalytic method, we should be able to generate new IP. Of course, these projects are always done in collaboration with somebody, and then it's always the discussion who has the IP on it, if it's a shared IP or the client might want to keep the IP to themselves.
Okay, thank you. And I think one last question for Marie. So far, there might be, they're still coming in. So besides the 1,3-dione, there are many other 1,3-cyclobutane derivatives shown. Is this something you are currently working on and will soon make available to everyone?
So yeah, on the slide, we show that we made the bench stable 1,3-dione salt. And we believe that this is just opening the door for many, many more options. At the moment, we're not studying them. The reason being that we are a CDMO partner, so we do R&D and focus on customer projects. On some topic, we have a proactive approach, and this is what's been discussed today. But this is not our main job, let's say that this way. If we see or if we hear that there is a specific need for one of this building block, we will be happy to look into it deeply. But on a first basis, this is not the topic we're digging at the moment. We are hoping a customer can now see it, will come to us, and we will develop this together.
Thank you, Marie. So I think that is all we have time for today. But as mentioned earlier, if your question did not get asked, a member of the Arxada team will be in touch with you. Thank you all for attending today, and a special thank you again to the Arxada team. It was a pleasure to host you. And I would also like to take the opportunity to invite you all to join us at Chemspec Europe in Frankfurt from the 31st of May to the 1st of June. So hopefully see you soon, and goodbye.
Thank you, everyone. Thank you, Lee, for organizing and hosting us. And yeah, very much looking forward to seeing you all in Chemspec in Frankfurt.
Thank you very much. Bye, everyone.
Take care,
Thank
everyone.
you.
Goodbye.
Bye.
Bye.
Bye, thanks.